Hello everyone, welcome to MLAS 700, Advanced Cybernetic Systems Development. This is Learning Activity 9, and we'll talk about limitations or machine learning limitations in this week's lecture before we hit the labs. And first up is just a review of what do we mean when I say limitations, and it's just like it sounds. These are things that we have to kind of take into account when we're talking about machine learning models, artificial intelligence in general, and then the delineations that are made in the limitations in the different types of system requirements, or the output of what the system's capabilities are. So, and when we say limitations, it's really talking about what we're talking about capabilities. And so the first one is a limitation around what we call dataism, and this is the idea that everything, humans, machines, we're all a product of our capacity to process data. And that is, as humans, we are data machines. We take sensory input, which is data. We take information from our eyes, we take from our surroundings, we take information from what we hear, and we process that. Our touch, we have chemical receptors as well in our tongue as well as our nose. And we take all this sensory information, and we are information processing machines as humans. All animals are, all the way from worms and bacteria all the way up to more complex organisms like us. And so there's so that's what we mean when we're talking about dataism, and that's the idea also behind machine learning models. They are bound by that as well. And so that's a limitation. Another limitation too is the idea of before I get to number 2, I do want to circle back on number 1 just for a second. Is that's a very cybernetic way to look at it as well. So when we're building a cybernetic system like what we've been doing or continuing to do in this course, and what you've been doing in the prior course in 650, is that the cybernetic loops, the inputs and outputs, and the management of a control system through a control loop in cybernetics, it only makes sense when that loop creates change. So in other words, if I come in with an input A and I get an output B, then that is what a cybernetic system is concerned with, is anything that affects change from one state to another. If it does not move in other words, if I have an input of A and an output of A, then I have an error in that system, so to speak. Not an error, but something that's not cybernetically bound, because there's no change that's occurring. So that's something that I want to talk about in terms of dataism as well. Okay, moving on to number 2 then, is this idea of deterministic versus stochastic. So when we are talking about deterministic machines, we're talking about things that are finite, that have, I shouldn't say finite, but just things that are procedural, and they're specific, and they don't move off of that predetermined route. Whereas stochastic, we're talking about a probabilistic function that can exhibit an ability to move off of that. Almost a very, very large percentage, and so this idea of maths being involved with artificial intelligence is why are they involved at all? Well, turns out for machine learning and for humans, we learn in this deterministic stochastic way. We actually learn in reverse. We actually learn stochastic and then deterministic, and then we bounce back between this idea of stochastic. It's a continuum, a spectrum between stochastic and deterministic. So think of it as when you're born as a human, you don't know how to walk, and that is something that you learn initially stochastically. So you do a trial and error, like move your leg right, move your leg left. You don't know this when you're that young because your brain isn't completely formed. It's still trying to form all the connections of everything that is your sensory inputs and motor functions, and just there's so much that's going on. But you learn. Let's just keep it isolated to just walking. Well, there's a whole. If you've ever seen a baby walk, it's in the beginning, it's a very trial and error process, right? I mean, there's this, move leg this way. Nope, that didn't work. Okay, move leg that way. Well, that didn't work, and it takes a year for the brain to get that figured out. Usually, and not always, but usually between 12 and 18 months, a human baby starts to learn how to walk. And that is stochastically driven. In other words, it's a probabilistic function of trial and error. And so, but as what's interesting about that is as you start to learn how to walk, it gets laid down procedurally into a deterministic framework within your brain, so that you don't have to think about it. So that's the idea behind the difference between stochastic versus deterministic. And then, and we'll talk through this. And then the third limitation is this idea of, again, it's back to dataism, but it's about the data and how much data and what data is available, and the biases that can be subject to what the data is that I'm injecting into the data. And so that's true of anything. That's true of human learning. If for example we talk about doing no harm when we're training, let's say, pilots to fly airplanes. Well, we want to teach them how to have correct procedures for when emergencies come up. And so in that training process of learning how to fly an airplane, a pilot is ingesting data. That's what the classroom is about. It's a data ingestion process. It's a training environment to create training data for the human mind. Remember, it's a biological computer, and so it needs data. Well, we don't want to introduce biases, or we don't want to introduce things that may influence or improperly impede on a pilot's ability to manage emergencies, as an example. So we have to be very intentional about the way that we handle training data for pilots, as an example. So that's limitation number 3. It's very real. And it has impacts and implications into our AI systems that are built today. Okay, well, let's talk about this first one here. This idea of dataism. I talked a little bit about this in the beginning, in that so another component, a big part of dataism is of course, yes, we are humans that are data centric, and that also means that we have to form a picture that allows us to trust data before we use it. And so it used to be, back in the day, the U.S. Navy, actually, as an example, U.S. Navy did celestial navigation and dead reckoning as their preferred certified methods for ship navigation. This is actually not too up to about 20-30 years ago is my understanding. And so it was something that there were GPS systems, but they weren't used in an official capacity. It just seems unheard of now, right? I mean, machines we've got it in our cars, we've got it in our phones, and so of course U.S. Navy ships have them now too, but they weren't allowed to be used because it was new tech and didn't trust the data. So that's what we talk about when we're talking about dataism in this case. Is the limitation of the systems is also the trust, and that's a very real thing that's happening right now. There was an emergency alert that went out. This was years ago. That was out in Hawaii. It said seek immediate shelter, and it's not a drill, and it really freaked people out, and this created a big problem back in 2021, I want to say, but regardless, I can be fact checked on that. But back then there was this incident that happened, and it created a problem for trusting data. Like I create a system, and then this thing happens, and then I've got a data trust issue. Same with healthcare, and it's coming up more and more. Do we trust AI? And there's a lot of pockets of a lot of different industries that are very fearful of AI, but there's also industries that are leaning into it. Military used to be fearful of it, now they're leaning into it. Aerospace, space, and they've been in physics, and they've in that astronomy community, they've been using artificial intelligence and AI systems for years, many years. And so there's a lot more trust in those areas, and scientific community, and anything that deals with any type of scientific computing in general as well is going to have more trust in the usage, and not be as fearful of using AI systems. And but nowadays, you start to see more of that found in higher education. And there's some fear in that world when it comes to AI. And so to a certain extent, we're kind of behind the curve as it relates to how fast the industry is moving versus how slow we're moving on the education side of it. But good news is this is a machine learning program you're in, so we aren't afraid of using them. So the last graphic down here, this GPS trust, it starts to become, there are certain functions that, while it would probably be better that an AI take over it, especially considering how large our large language models are now, there are some interesting implications for, well, wouldn't it make more sense to have an AI who has way more precedence and an understanding of law to be an artificial intelligence as a judge versus a human as a judge? I mean, because humans, let's not forget, humans have biases, right? We have them through our training data. And so it's not to say that large language models would be perfect, but they're much better at it than humans are in that bias department. So in a way, it probably makes more sense for there to be AI judges as an example. Because that's the ultimate in fairness and equity, of course. Again, still there's a bias there that we have to be able to spot. But ultimately, we know that, well, humans exhibit biases today. So that's definitely an area for research. And a limitation. So within the AI research community. So the number 2 is the deterministic problems versus stochastic problems. So this is a Python program that's just a sine wave. And what I've done is created, this is just one that I created years ago. And it's a very simple idea. It's a sine wave that has some stochastic points that are around it. And so this is a great visual representation of the idea behind deterministic versus stochastic. So the blue dots represent stochastic data. The cyan dots represent stochastic data. And because they approximate, sometimes they fall on the line, but sometimes they fall off the time. Often they fall off, but it's their pattern and their ability to not be on the line that is very key here. That is what makes stochastic work well. And then is when I need to deviate from what it is that I see in front of me, I need to have a stochastic machine that can think or exhibit an ability to move beyond deterministic programming. And that can only be achieved through stochastic probabilistic programming techniques. But once I get good about what it is I need to do something over and over and over and over again, then I don't need a stochastic framework. I don't need a stochastic machine learning framework at that point. If I needed to do it over and over again, I need to switch to a deterministic framework, and then it's very precise, and it always works on that specific line or a particular path. a particular output that I'm trying to affect, and I wanted to do it with perfect precision, with high frequency regularly. That's something that you want to do in a deterministic environment. And you'll probably say, well, how does this apply to, the industry? Well, it has a lot of implications, actually, like how I build robots, what I do, is it a deterministic robot versus a stochastic robot? Do I have a process? Is it image classification? Is this, do I want to have a little bit more wiggle room to pull data from a vision system? Well, then that might be a stochastic, it might be deterministic with some elements of stochastic built in. So it has to be considered. So with that said, if you take a look at the maths that are involved between everything, whether it's deterministic, stochastic, or semi-stochastic, or semi-deterministic, depending on your perspective, AI frameworks are using. If you're in a deep learning world, it's a linear algebra, multivariate calculus, but very linear algebra heavy. Whereas if you're on, you're outside of the neural network and you're not doing deep learning, you're getting into probability theory and statistics. Probably pretty heavy on that side of it. But taken together, linear algebra, probability theory, and statistics make up a super majority of the math involved, and then of course calculus has 15% there. And whenever, if you're going to be building most modern systems have a combination approach. It's not just a one size fits all. So oftentimes we'll be on the hook for building a system that has multiple models to it, not just one. And that helps for a number of reasons. It makes the model more robust for the environment that we're trying to code it for. It makes life easier for us for more complex scenarios when we have ensemble methods that take into account both stochastic and deterministics. In other words, semi-stochastic or semi-deterministic systems. Okay, so just that's something to keep in mind. The last limitation that I want to talk about here is data. So when we're creating large language models or open knowledge graphs, GPT is a large language model as well, but I use large language models as kind of a stand-in there for the more generic open source models like Mistral or Mixtral. What's the other one? Llama, that's one that we've worked with. And these large language models, the parameterization requires they're so large, but to the degree that it takes so long to train these models on, the compute power is just amazing what it takes to build some of these. But regardless of the AI system, whether it's a large language model or a structural equation model or a random forest, they all require quite a bit of data. And that is very, very true. It's a limitation, and it requires data. You can't create these models without having some form of data available for training purposes. Moving on to the next one is there's a less intense version of this from a data requirement, and there are machine learning models that are focused on tiny ML, which is, guess what? That's our world. So we're going to be working on tiny ML that are like this machine learning micro models. And so we'll be learning about those heavily in this course. But it's helpful to know that there are other less intensive. There's physics-informed neural networks. There's also neuromorphic learning methods. But physics-informed, they're called PINs, P-I-N-N. But physics-informed neural networks is an interesting phenomenon from a model perspective because it takes a neural network and then combines it with math. So in other words, if I know how gravity works, then I can take that gravity and the calculations that go into gravity, and that is something that it goes and gets baked into the neural network, and then the neural network is using what's called a physics-informed perspective on its output. So it takes an algorithm of an algorithm. The algorithm takes another algorithm, and that is the physics-informed nature of the world around it, like how gravity operates. Okay, here's how that works, and then here's thermodynamics and the calculations for that, and then okay, now feed that through the system, and then give me an output. So these are kind of nice because they operate on a much lower, smaller footprint. Okay. Well, I think that's all I've got for this lecture. It's just again, this is just kind of machine learning limitations. Again, we're working our way up towards more complex topics here. But that's all we've got for now for the lecture. And if you've got any questions on this, of course, let me know. But we are going to be switching over to a lab, and so you'll want to get your kit out and get ready for that. And I will see you with that. I'll actually see you in the lab. Okay, take care.